about now? Okay. So far in today's session, we've heard about axion dark matter, we've heard about self-interacting dark matter, but today I'll be talking about missing dark matter. And so in particular, I'll be investigating the claim that NGC 1052 DF2, an ultra-diffuse galaxy, has a deficit of dark matter. So ultra-diffuse galaxies, just to preview this afternoon session talk, these are galaxies with the luminosity of dwarfs and the sizes of giant galaxies. So over here we have an ultra... Oh, it is necessary because if you looked at that, that's just a galaxy of only dark matter right now. Okay, so now you might even be able to see that this over here does indeed have some stars. So this is an ultra-diffuse galaxy on the same physical scale as Andromeda over here, of course, our nearby giant galaxy, and a more normal dwarf elliptical galaxy. So a natural question is, in what sort of halos are UDGs found? Are they failed giants, or are they dwarfs that have been popped up? So what do we know about UDGs? We find them in a range of environments, often in clusters, but we do find them in the field as well. They generally have old ages and low metallicities, at least specifically in the cluster UDGs. And most relevant to this talk, we infer a range of halo masses for these UDGs. So in this plot from Toloba et al. In 2018, we're looking at the dynamical mass-to-light ratio as a function of dynamical mass. And in this narrow mass range here, around where you see the dwarf ellipticals, the UDGs here, these red and blue points, there's a huge, over an order of magnitude range in that mass-to-light ratio. So DF2 was first noted as a smudge in the plates in the late 70s, but first really cataloged by Karachentsev in 2000. And so here we see the central giant galaxy, NGC 1052. This smudge over here is DF2. And if we zoom in, some of these point sources that we see around the galaxy are actually star clusters associated with DF2. So Van Dockum et al. Took spectroscopy of several of these star clusters using KEK-DEMOS and LRES. And so from spectroscopy, looking at calcium triplet absorption lines, we can get radial velocity measurements for these star clusters. And this led to a bit of controversy here. We're looking at now the different velocity measurements as a function of position in the galaxy, and then in this histogram just collapsing down into what is that distribution of velocities. And then if you squint and try to associate a velocity dispersion to that histogram, you get something on the order of 8 kilometers per second. And that would imply a dynamical mass-to-light ratio of around 2. That number is consistent with most of the mass, most of that dynamical mass being only comprised of stars. So in other words, this galaxy would be missing, would be lacking in dark matter, missing, having a deficit, however you want to describe it. But there was a lot of concern about this measurement. And so one of the concerns would, of course, be about the small number of tracers that you're using to make this measurement. So we have 10 tracers of the potential here. And this concern was well illustrated by Martin et al., who showed that if you took M31's globular cluster population, you just keep on sampling 10 velocity points from that data set, and you calculate your velocity dispersion. You get this histogram of possible samples of your velocity dispersion. And the concerning thing is that the bottom quintile or so of those samples you would get would say that N31 is missing in dark matter, that it has around the same order of dark matter as its stars. So we have to take this into account when trying to interpret this thing. So we did Jeans modeling of NGC 1052 DF2. Our goal is to infer what range of halo masses are permitted by the data. And so we use a fully generative Bayesian modeling framework. This allows us to do a number of good things. For one, we have an explicit treatment of our priors. And here, the interesting thing we're going to focus on is we're going to explore models both with and without a prior from a stellar to halo mass relation, including an explicit model for increasing scatter at the low mass end in the stellar to halo mass relation. And we're going to want to compare these different kinds of models, but we can only do that in this Bayesian framework. It also allows us to marginalize over sources of systematic uncertainty in trying to map the kinematic data to an actual mass. So what are the results of these models? So when we include a strong prior on there being an expected amount of dark matter from the stellar to halo mass relation, we get that in the inner 10 kpc, we have around 10 to the 9 solar masses of dark matter. When we relax that prior and we say that the dark mass can be decoupled from the stellar mass, we're introducing a little bit more model freedom here. And when we look at that model, we get over an order of magnitude less dark matter. In fact, less than the amount of stars that we see. So how does that look compared to the data? Now we're looking at velocity dispersion profiles compared with the actual discrete velocity points. These are actually the absolute deviation from the mean, are these black points for the actual data. And the way to interpret this is if we look at this blue line, which shows the model with the strong prior and there being lots of dark matter in this galaxy, we would expect, if this is the true sort of 1 sigma line of velocities, that around 2/3 of the velocity points should be below that line. And hardly any of these velocity points are above that line. Whereas when we have the weak prior, we see that 6 out of 10 points are below that line. So if you squint, this model looks like it has more predictive accuracy, but we do have to be careful when doing inference in a prior-dominated regime. We have to properly take into account model complexity when we're evaluating different models. So we do this with the Watanabe-Akaki information criterion. You can think of this as a fancy Bayesian reduced chi-squared, where we have our measure of predictive accuracy. We have a quantification of the effective degrees of freedom in the model. When we do that, we find model odds of around 2 to 1 in favor of this low dark matter model. So even after accounting for model complexity, we would prefer the model with low amounts of dark matter, but this isn't anywhere enough to completely reject the normal dark matter model. So what is this thing if it does have very low amounts of dark matter? One proposal was that DF2 could be a tidal dwarf. This was explored in a scenario by Ogia. And here we're looking at the orbit of DF2 around NGC 1052. And you can get the expected amount of dark matter in this scenario. But the problem is this is actually a very rare orbit in lambda CDM, very tightly bound, very radial. So if we were to find anything else that looks like DF2, this would be a less likely scenario. And if we try to compare things with the local group, what does that look like? Here we've created a diagram to quantify the mismatch between the measured or inferred halo mass and the expected amount of dark matter that you would see. So the y-axis is the circular velocity attributable to the dark matter. So we take our dynamical mass, subtract the stellar mass at the circular velocity. The x-axis is quantifying the spatial extent of the tracers used for that dynamical mass measurement. Here we've got the local group field and satellite dwarfs, and here we've got DF2. So if DF2 was a tidal dwarf, the closest local group analog would be Andromeda 19 over here. This is where we'd expect to find the dark matter mass of Andromeda 19, taking our usual stellar to halo mass relations. And here's where we'd expect to find DF2 in the normal expected amount of dark matter scenario. And so this offset is much greater for DF2 than it is for Andromeda 19. And that's really just because there are over 2 orders of magnitude more stars for DF2 than there are for Andromeda. And so we really don't have a great local group analog of DF2 if it is something like a tidal dwarf. So to wrap things up, we're still in the dark. The available data for DF2 are consistent with and do favor a low dark matter model for the galaxy, but it's also allowed for there to be a normal dark matter halo. And crucially, this depends on the priors one adopts. If we do believe in the low dark matter model, it's difficult to explain DF2 through a tidal stripping scenario. And just to end on a very speculative note, this may indicate that there's more scatter in the stellar to halo mass relation at the low end than models calibrated to the local group might imply. Thanks.
Great. Let me ask Victor to come up and start plugging in. Joel?
Quick question about the objects that actually have the velocities.
Mm-hmm.
They're called boundary clusters, but they're weird.
Yeah.
They're all really bright. As Dean Brody pointed out when we discussed this globally, with each one of those bright ones, there could be at least 10 more fainter ones that we don't see. So what's going on with this object?
I don't know.
So many quote-unquote globular clusters that
So,
don't seem to be a normal globular cluster population at all.
notice I never actually called them globular clusters. I called them star clusters. And so we see a very weird luminosity function for these objects, where they're not only very massive, more akin to like an omega Sen kind of object, but they're also, it's a very narrow range. So there are some crazy scenarios out here where these could be merged globular clusters. I don't really know, and I think really if we wanted in this particular case to narrow down a formation scenario, we would need to do so by understanding the origin of its star cluster population, but I don't have a good answer for what they are.
Okay. Really quick.
So I don't think we have 10 minutes to talk about all the different distance measurements. But the main, I'm not an expert in the distance stuff, but I've been convinced that the evidence is stronger for a 19 megaparsec distance. One of the main claims for saying it's at 13 megaparsecs is this claimed detection of the tip of the red giant branch. And there's pretty convincing evidence that it's more likely to be explained by blends of stars that can give you this phantom tip of the red giant branch effect. There's like 4 other distance things. We could talk about it later. You probably want the microphone before I run off with that. You hear weird conversations in the back.